So we could actually find theoretical expressions for the autocorrelations of an AR2 model using its coefficients. So what do we mean by that? Consider an AR2 model, and what do we mean by that? It's xt equals phi1 xt minus 1 plus phi2 xt minus 2 and plus some noise component at. And for an AR2 model, we have the Ewell-Walker equations, which is ρ1 equals phi1 plus ρ1 phi2, and ρ2 is equal to ρ1 phi1 and phi2. So we want to solve for the autocorrelations. So if we look at the first equation, we could rewrite ρ1 minus ρ1 phi2 equals phi1, which would imply ρ1 times 1 minus phi2 would equal phi1. ρ1 would then equal to phi1 over 1 minus phi2. And likewise, if we take the value of ρ1 and plug it in the second equation, and we would have ρ2 equals phi1 over 1 minus phi2 times phi1 plus phi2, which is phi1 squared plus phi2 times 1 minus phi2 over phi2. So that would be the expression for ρ2. So we could either leave it as is, or we could write it as phi1 squared minus phi2 squared plus phi2 divided by 1 minus phi2. So if we have the coefficients, we can find the autocorrelation using the formulas that we derived just now. So here is an example . We want to find the autocorrelations of the AR2 model and the variance of noise if gamma naught is 1. So let's say the model is xt equals 0.75 xt minus 1 minus 0.25 xt minus 2 plus at. So we know the values of phi1 and phi2, phi1, phi2, so since we know phi1 and phi2, contrary to the previous example where we had the values of the autocorrelations and we fit the model. Here we have the coefficients and we are trying to find the autocorrelations. So rho 1 would simply be given by that formula, phi1 over 1 minus phi2, which is 0.75 divided by 1 minus 0.25. Get 0.75 over 1.25. And that turns out to be 0.6. And rho 2 is phi1 squared minus phi2 squared plus phi2 divided by 1 minus phi2. So 0.75 squared minus 0.25 squared minus 0.25 divided by 1 minus 0.25. And that would give us 0.25 in the numerator, 1.25 in the denominator. We have 0.2. So in a calculation like this, if you determine the values of rho 1 and rho 2, and by some chance you have rho 1 and rho 2 exceeding 1, then there is a mistake somewhere, because we know that autocorrelation cannot exceed 1 or cannot go below -1. So that said, we can't find the variance of the noise, so we have our usual formula. Sigma squared x is equal to the variance of the noise divided by 1 minus phi1 rho 1 minus phi2 rho 2. Since the value of sigma squared x is 1, so we have 1 times 1 minus phi1 rho 1 minus phi2 rho 2. And here we have the coefficient values as minus 0.75 and rho 1 is 0.6, which we computed, and minus 0.25 for phi2, and rho 2 is 0.2. So if we plug that all in, we end up getting 0.6. So the purpose of this particular example is to realize that if we have the coefficient values, we can find the autocorrelations using these two formulas, which is rho 1 equals phi1 over 1 minus phi2, and rho 2 is equal to, I didn't mean to do that. I'll erase. Plus phi2, and we could find rho 2 using that formula. And once we have the autocorrelation values and the coefficient values are given in the problem, such as here, we have 0.75 for phi1 and negative 0.25 for phi2, we can readily plug that in the noise variation, variance formula, and we can find the variance of noise as well. That is a good place to stop.